This video will teach you how to solve the College Board AP Chemistry Free Response Question 2 from 1997. Part A asks, what volume of 0.400 molar NaOH is required to neutralize completely a 5.00 times 10 to the negative 3 mole sample of pure oxalic acid? The balanced chemical equation between the acid and the base is written as 1 mole of oxalic acid plus 2 moles of the sodium hydroxide produces 2 moles of water and 1 mole of sodium oxalate. The net ionic equation is shown as the H2A plus 2 OH minus produces 2 waters plus 1 A minus. The H2A represents the oxalic acid because it is a weak acid, and the A minus represents the C2O4 negative 2, which is oxalate because it is the salt of the oxalic acid. To find the volume of base needed to completely neutralize the oxalic acid, the 5.00 times 10 to the negative 3 moles of oxalic acid can be multiplied by the 2-to-1 ratio of hydroxide to oxalic acid that is found in the balanced chemical equation. This is then multiplied by the molarity of the sodium hydroxide to give the amount of NaOH needed to completely neutralize the sample of pure oxalic acid. The final answer is 0.025 liters of sodium hydroxide. Part B asks for you to give the equations representing the first and second dissociations of oxalic acid, then to calculate the value of the first dissociation constant K1 for oxalic acid if the value of the second dissociation constant K2 is 6.40 times 10 to the negative 5. K represents dissociation. Since oxalic acid is a diprotic acid, meaning there are 2 hydrogens, there must be 2 dissociation constants. The K1 is written as oxalic acid produces 1 hydrogen ion and 1 HC2O4 negative. The K2 starts with the product of the first as this HC2O4 negative, then produces 2 hydrogen ions plus the C2O4 negative 2. The overall Ka is the combination of the K1 and the K2, and is shown as the oxalic acid producing 2 hydrogen ions and the C2O4 negative 2. To solve for the K1, the K2 and the Ka must be known. The K2 was given in the problem as 6.4 times 10 to the negative 5. The Ka was originally given as 3.78 times 10 to the negative 6. The K1 can then be found by dividing the 3.78 times 10 to the negative 6 over the 6.4 times 10 to the negative 5 to give your answer of K1 equal to 0.0591. Part C asks, to a 0.015 molar solution of oxalic acid, a strong acid is added until the pH is 0.5. Calculate the concentration of the C2O4 negative 2 in the resulting solution. Assume the change in volume is negligible. Since the strong acid is added, it is going to be represented as the H3O+. Since 2 acids are added together, H+ is a common ion, so the equilibrium is shifted. However, no reaction takes place. This is also demonstrated as the products of this reaction, as well as the Ki, are the same as are in the given overall equation. There's the concentration of H+ in the Ka expression is squared because there's a 2 coefficient in front of the H+ in the balanced equation. The question asks to find the concentration of the C2O4 negative 2. The Ka is given in the original equation as the 3.78 times 10 to the negative 6, and the H2A concentration is given as 0.015. The H+ concentration must be solved for. Using the pH equal to 0.5 and taking the anti-log of the negative 0.5, the concentration of H+ is determined to be 0.316. Plugging that in for the H+ concentration and squaring it will allow you to solve for x. The x represents the concentration of the C2O4 negative 2. That value is equal to 5.68 times 10 to the negative 7 molarity. Part D asks you to calculate the value of the equilibrium constant, Kb, for the reaction that occurs when solid Na2C2O4 is dissolved in water. The products of the sodium oxalate dissolved in water are shown as 2 sodium ions and 1 C2O4 negative 2 ion. The C2O4 negative 2 ion reacts with the water to produce an HC2O4 negative and an OH minus. In this equation, the HC2O4 negative acts as an acid as it donates a hydrogen to the C2O4 negative 2, and the C2O4 negative 2 acts as a base as it would accept the hydrogen. Therefore, the HC2O4 negative will give you the Ka, and the C2O4 negative 2 will give you the Kb. The Ka of the HC2O4 negative was determined in Part B as it represented the K2, as it was represented by the K2, which was given to you as the 6.4 times 10 to the negative 5. Kw is known to be 1 times 10 to the negative 14, so using the equation Kw equals Ka times Kb, the Kb can be calculated by dividing the 1 times 10 to the negative 14 over the 6.4 times 10 to the negative 5 to give you your answer of 1.56 times 10 to the negative 10 is equal to the Kb. And I will thank you very much.